Okay, good morning, guys. All right, questions. Which problems did you have trouble with? Unmute and speak up or chat and write me the numbers. Go ahead. Can you hear me?
Yeah.
Yeah, okay, questions.
Maybe this is just me forgetting how to math, but on 57 and 61, you've got to solve for the absolute value with an inequality, and I just couldn't get that to work.
Okay, let us remember that. I will start by reminding a little bit. Suppose we have the following. If I tell you find all values of x such that the absolute value of x is less than 2. Okay, so what is x? So let us find values of x that satisfies the absolute x less than 2. So will 0 work?
Yes.
Will 2 work?
No.
Will -2 work?
Yeah.
-2.
Yes.
All right, let's check it. Suppose take x equal -2. What's the absolute value?
No, it won't.
Exactly. Absolute value will become equal to 2, so that x cannot be equal -2. Now, what about if I take x to be, let us say, -1.9? Would it work?
Yeah.
So what are all the x's that satisfy absolute x is less than 2? Where x should be? X cannot be larger than 2, and x cannot be less than -2. It means x has to be between 2 and -2. So if the absolute value of x is less than 2, it means x has to be between -2 and 2. Anything larger than 2, of course, its absolute value is going to be a lot bigger than 2. And anything smaller than -2, like -3, -2.5, when you take them in absolute value, they are going to be definitely larger than 2. So absolute x less than 2 means that x has to be between -2 and 2. So in general, what is the rule? If you have absolute x less than a, so let a be a given number, it means x has to be between the positive a and the negative a. That's what it means. All right, make any sense? Okay, now what does it mean, the absolute value larger than a? How can this happen? If the absolute value larger than a, it means that either x larger than a or x less than -a. So on a graph, if this is 0, this is -a, and this is a, if the absolute value of x is larger than a, it means x is either here or it's right there. That's what x is. Absolute x less than a, it means this is your number line, this is a, this is -a, it means x is in here. So absolute x less than a, that's the picture. Absolute x larger than a, it means that's the picture right there. So that's how you work with the absolute value. Is it making any sense? Greg?
Yeah, but the problem that I was running into was, so 2 over x is less than 1.
Right, we're going to work with that. So your question will become 57 and 61, correct?
Yeah.
Okay, this is Greg's question. How about anybody else? Any other questions? So we can go through them in order. Okay, you guys are comfortable? Fine. So I'm going to do Greg's question, and I'm going to do number 25. And then I will do both 57 and 61. So number 25, we have the following sequence, the following series. Sigma n equal 1 to infinity of the following. E to the 2n over 6 to the n minus 1. Now they tell us, they tell us basically to, first we have to find the ratio, because they tell us it's geometric, and we're gonna find the ratio in two ways. The first way I'm gonna find the ratio is by writing up the terms and see what is the common ratio. That's the first way I'm gonna do it. So I'm gonna write up the term. So if n equal to 1, I'm gonna have e squared over 1 basically, plus e to the power 4 over 6, plus, if I take, so this is n equal to 1, this is n equal to 2, now n equal to 3, I'm going to have e to the 6 divided by 6 squared, plus I will n equal to 4, I'm going to have 2 times 4, that's e8 over 6 to the power plus, and so on and so forth. So now the first way I'm going to do it is just by writing up the first few terms and see what is the common ratio between them. So what's the common ratio? It means when you go from here to here, what are we multiplying by? Who would like to give me an answer? I want an answer. Somebody has to give me. What is the multiplier? What are we multiplying by? What are we multiplying e squared by to get e4 over 6? Anyone? Okay, somebody told me. Yes, I know. E squared over 6. Is she correct? Take e squared multiplied by e squared over 6, you get e4 over 6. Now, does this ratio continue? It means if I take e to the 4 over 6 and I multiply it by e squared over 6. Okay, e4 times e squared, that's e6. 6 times 6 e squared. So that's really the same thing. So the common ratio here, the common ratio is e squared over 6. And the first, so e squared over 6 is how much? Is it bigger than 1 or less than 1? Most probably bigger than 1, right? Because what is e squared? E squared is like almost 7 point something. So e squared is, so it's 7 point something, if my memory is correct, divided by 6, actually more than that. Okay, so this is definitely a number which is bigger than 1, which means that my series diverges automatically. All right? Any question? Yeah. So now that's one way to write it as a geometric series. Write up the term and see what's the common ratio. Now, sometimes you can rewrite this. We can juggle a little bit the notation to see it as a times r to the n. So how can we juggle the notation a little bit? Just out of practice. So I'm gonna write it like that. So I rewrite the series in front of me again so you guys can see it. And I'm gonna juggle a little bit the notation just because we can. All right, so my goal is to write it clearly for you as sigma a times Rn. So you can see it clearly as geometric. So how can I juggle that? How can I bring Rn to the picture? So 1 to infinity. This is gonna become e squared. I'm gonna write it as this way. And the bottom one is 6 to the n times 6 to the minus 1. So that's how we can juggle a little bit. And now we can arrange those terms, and this is going to become 1, basically 1 over 6 to the minus 1. I know this is 6. And you will have e squared over 6, the whole thing to the power n. So this is a good exercise in practicing juggling notation. So finally, I can rewrite this as 6, because 1 over 6 to the minus 1 is 6, e squared over 6 to the power n equal 1 to infinity. And now by writing it this way, we see again that my common ratio is exactly e squared over 6. So you can either write up the terms very clearly and look what's the common ratio between the terms, figure it out, and then decide. Or you can basically rewrite it, juggle a little bit the notation, and like I did below, and find the ratio. All right, now we look up at number 57 and 61 a little bit.
Professor?
I'm listening.
How was that the same if the first term was e squared? Oh, never mind. I see it.
Okay, thanks.
Sorry.
You're fine, no problem. Okay, let's look at 57. Okay. 57 is, we have the following series. Sigma n equal 1 to infinity of minus 5 to the n times x to the n. And the question is, for which value of x? For which value of x does this series converges? Now, the only thing we know so far is geometry. So we want to write this as a geometric series first. So I'm going to rewrite it as a geometric series. And this is not hard to rewrite as geometric series because I just can combine those two terms. To infinity. Okay. Now, you can either look at it and say that the ratio here is minus 5x, or if you want, you can start writing the terms. So it's minus 5x plus minus 5x squared plus minus 5x cubed plus etc. and realize that the ratio here is minus 5x. Okay, so the question is, for which x's? Which x can I put here which will allow the series to converge? So by the test we saw yesterday, here the ratio is minus 5x. It means that the series, the sums basically, the partial sums will become close to a fixed number when the series converge, when the ratio, it means absolute value of minus 5x is strictly less than 1. Questions so far? And now the question is, how can I pull the x? How can I find the condition on x? Okay, one of the properties of the absolute value is the following. If you have a times b, that's product of the absolute value. The absolute value of the product, you can actually split it. It's the absolute value of A times the absolute value of B. So now I have two terms. What's the absolute value of minus 5x? So that's the absolute value of minus 5 times the absolute value of x. Now, absolute value of minus 5 is the same as absolute is 5. It means 5x is less than 1, which means that absolute x is less than 1 over 5. And now the question is, what is x? If the absolute x is less than 1 over 5, it means x has to be between 1 over 5 and minus 1 over 5. So if you take a value of x, which is between minus 1 over 5 and 1 over 5, you plug it in here, the series will converge. If you take anything which does not satisfy this property, the bottom property, then this series up there will actually diverge. That's how we handle this problem. Please ask questions before I move on to 61. Anyone? Any questions? All right, so finally I look at 21 and then we proceed. So let us look at number 21. Okay. I meant 61. Number 61. And this time I have the same type of questions, but the series is sigma n equals 0 to infinity of 2 to the n over x to the n. So I'm gonna rewrite this as sigma 2 over x to the power n, because it's actually kind of simple here to see the common ratio. So the common ratio here, the common ratio is 2 over x. So now I'm gonna do exactly what I did before. So my series converges when absolute value of 2 over x is less than 1. Now again, I'm going to use the properties that I mentioned a minute ago. So absolute values also have the following property. The absolute value of a over b is the absolute a over the absolute value of b. So we can rewrite it this way. And this is going to help us in this problem, because this will become the absolute value of 2 over the absolute value of x is strictly less than 1. And this is going to give me 2 over absolute x is less than 1. Now I want to solve for x. Now this means that 2 is less than, I multiply by absolute x both sides. 2 is less than absolute x, or absolute x is greater than 2, but that's easier for us to see. Now, when is the absolute x greater than 2? It means this happens when x is larger than 2. Just think about it, or x is less than minus 2. So if I take a value of x bigger than 2, like if I take x to be 3, and actually it makes sense, watch carefully. If I take x to be 3, 2 over x will become 2 over 3. So this is really bringing up a ratio which is less than 1. If I take x to be 4, again, 2 over 4, 1/2, my ratio is less than 1. However, if I take x to be 1, it means x does not satisfy my condition down here. If x is 1, I will have 2 to the n, definitely diverges. So basically my question is, what can I put in here to force the series to converge? What I should put in here should be either less than 2 or bigger than 2 or less than minus 2. All right, questions before we move on to the new material? Questions about the problems? Okay, can I move on? All right, so today we're gonna talk about the following idea. Basically, what does the convergence of the series? So if I know that the series converge, what does this tell us about the sequence of terms? And if I know something about the sequence of terms, what can I say about the series? So before I read the theorem, I will ask you the following question, just to motivate, because I don't do proofs, but I try to motivate the idea. Suppose I take the following series, sigma 1 and equal 1 to infinity. Okay, so what are the terms here? I want answers. Just either say them or write them for me. What is the terms? It means what is a n in this scenario?
1.
1. You agree with her? They are all 1. So what is the sigma 1? It means I'm taking 1 plus 1 plus 1 plus 1, whatever. Okay, does the series converge or diverge? What do you think?
Converge.
Converge, why it converge? If we look at the partial sums, remember, series converge if the sequence of partial sums converge. What are the partial sums in this problem? What diverge? Exactly. What is S1? 1. What is S2? 1 plus 1. You see it? What's S3? 1 plus 1 plus 1. 3. What is S4? 1 plus 1 plus 1 plus 1. It's 4. You see what's happening? And so on. So what is Sn? Sn is n. So definitely the partial sums goes to infinity. So an is 1, but the partial sums you're adding 1, you're adding more ones, more ones, more 1. Definitely, this is gonna blow. So this series absolutely diverges. All right. Whoever answered that question, is it clear why it diverges? Now, part 2. Let us say I take the following series. It's a little bit harder, but which is okay. I'm gonna take the series just to motivate the theorem that I put on the notes. N over n plus 1, n equal 1 to infinity. Okay, that's my series. And intuitively, we're gonna decide whether this converge or diverge, very intuitively. Very soon we will learn exact ways of deciding those facts. What is the an in this scenario? What is the an? What are the terms here? Okay, the terms, when I say what an mean, I mean what are the terms? It means when we are writing this up, so this is like become 1/2 plus 2/3 plus 3/4. These are the terms I am adding, etc., etc. Plus like 100 over 101 plus 101 over 102 plus etc. This is the terms I'm adding. So when I'm asking you what's an, I actually am asking you what's this term here. These are the an. These are the terms. And the series is we are adding those terms. Now, what do you think? Does the series converge or diverge? I want you to look at it carefully and purely intuitively. What can we say? Look at it.
It converges.
Because everybody's telling me converge. And I'm getting converge to 1. Converge to 1.
It's because the ratios get closer and closer to 1.
So you're talking about this sequence, an.
Yeah.
Converges to 1, absolutely correct. So we're done with the sequence of terms. Now my question is about the series itself, not the sequence of terms. We are gonna make always a distinction between the terms and the series. The terms goes to 1, you're absolutely correct. Now, how about the series itself? It means when I'm gonna start adding those terms. And I repeat, I'm doing this very intuitively. Do you think when we start adding, the series will converge? First of all, is this geometric?
No.
No, absolutely not. Absolutely not geometric. Do you think this will converge or diverge? I'll give you 2 more minutes. What do you think? I'm getting diverge. What?
Yeah, diverge.
Diverge because?
Because you're still adding numbers. Numbers aren't getting smaller.
Exactly. What type of numbers I'm adding? This number is almost how much?
Almost 1.
Almost 1. This number is almost how much?
1.
1. So what am I adding eventually? 1 to 1. Even if I keep going, I'm adding 1. If I keep going, I'm adding 1. So eventually what I'm doing is I'm adding 1 plus 1 plus 1 plus 1 plus 1. This definitely, this series is gonna diverge. Very intuitive, but that's give us an idea what's really happening. Now, let us say, for the sake of talking, let us say that I give you the following, and then the theorem will become very clear, intuitively clear. Suppose instead of n, I put over 2n plus 1. So my term here are n over 2n plus 1. These are the terms. This is not the sum. That's the terms. Now, when n becomes close to infinity, those terms are going to be close to a half. That are the terms. Now, what about the series itself? You think it's going to converge or diverge? So let me write up some terms. Now I'm thinking about adding the terms. So it's a 1 over, I will have over 3 plus 2 over 5 plus 3 over 7 plus dot, dot, dot. So at some point, I'm going to hit like 100 over, so if n equal 100 over 201, and then 101 over 101, so it's going to give me 102, sorry, 3 plus dot, dot, dot. Do you think the series converge or diverge? Okay, I'm getting diverge, I'm getting diverge. Who would like to justify why it diverge? Anybody feel comfortable? Sarah, would you like to tell us?
Essentially, you're gonna be adding a half plus a half plus a half.
Exactly, she's absolutely correct. We're adding a half plus a half plus a half plus a half is going to diverge. Okay, so this is a motivation for the theorem so that it will make sense to you. So this is where I'm starting. So what does this mean? So if a series converge, then the terms should become very small. Then the limit as n tends to infinity of an is equal to 0. Does this make intuitively sense? Because if the terms don't become small, like they become close to 1, I'm going to be adding 1 to 1 to 1 to 1. The series will diverge. If the term become close to a half, I will become adding a half, a half, a half, and the half, the series will diverge. So if the series converge, it means the an have to be very, very, very small. It means the terms here, I need a paper, sorry. So this is my series, sigma an. And my pen ran out of ink. So this is my series, sigma a sub n, which is a1 plus a2 plus a3, etc. an plus 1 plus so on. If my series converge, those terms has to become very small. The terms have to become very small, because if those terms stay large, I will be adding large plus large plus large plus large. It means my series will diverge. So if a series converge, if we know it's converge, then those terms will have to go to 0. The series converge somewhere else, but the terms have to become very, very small. Otherwise, it cannot converge. And this is, it's actually an important fact, and let us talk a little bit about it. So, my question now, so if a series converges, then the terms goes to 0. However, if the term goes to 0, does this mean does the series converge naturally? And the answer is absolutely no. So if the terms become small, this does not guarantee that the series converge. If the terms become small, the series may converge or diverge, and that's very important. If it converges, the term has to become 0. But if the terms become very small, I have no idea how the series is behaving. It can go either way. So I'm giving you now here 2 examples. So these are the notes that you guys have on Blackboard, so you just listen to that. Let me consider the series, sigma 1 over 2 to the n. Does the series converge or diverge quickly? I want a quick answer because you should know the series by now. Does the series converge or diverge? Anybody? Converge because what type of series is that? What type of
It's
series?
geometric.
It's geometric. So exactly. So here the an is 1 over 2 to the n, which we can write it as a half to the power n. Okay, this is an. Now, as n goes to infinity, the an goes to 0, because when n becomes very large, 2 to the n becomes very large, 1 over it becomes very small. And the series converge because it's geometric with ratio equal 1/2. So that's one scenario where the terms become small and the series converge. But I'm telling you that when the terms become small, we can have both scenarios. So example number 2 is another scenario. But here I'm telling you always be careful. The term go to 0, but the sum is equal to 1. It means the partial sums converge to 1. The terms 0, but the sum is 1 because that's a geometric series. Now, example number 2 is, let us consider the following series. Sigma 1 over the square root of n. This is 1 plus 1 over square root of 2 plus 1 over square root of 3 plus 1 over square root of 4 plus etc. The an here are 1 over square root of n. These are the an. The an are those terms. The an. When n goes to infinity, what happened to the an? Do they go to 0? When n goes to infinity, square root of n goes to infinity. 1 over something very large is very small. So the limit goes to 0. However, this series diverges. So even though the terms become very small, and that's what makes this very hard, even the terms are becoming very small, but intuitively what's happening, they are not small enough. It means when you start adding them, they keep adding. And the series will diverge. Now, in the next section, we will learn exactly how to do it. But for now, I'm just going to show you some values of the series. So I just computed the sum. So this is, if I take n to be 10, so it means I add 1 plus square root of 2 up to square root of 10, I get 5. If I add the first 100 terms, I got 18 point something. This is not a proof, but this just gives you an idea what's happening. If I get the first 1,000 terms, even though those are very small, the terms are very small, like 1 over square root of 10,000, this is a small number, but still not small enough. And I still add up a bit at a time. I added the first 1,000 number, I got 61. I added the first 10,000 number, I get 198. If I kept going, actually, I realized that those terms, those sums, I keep blowing up and blowing up and blowing up. We're not getting close to anything fixed. The sums are becoming larger and larger and larger. So even though the terms are small, and not small enough to be able, not very small, so when we're adding them, they are still, every term is still contributing a little bit to the total sum. Every term contributing a little bit, eventually we are blowing up. So that's going to be really our main problem for the next 3 sections. So if the terms become small, the series may do both. So the question is, how are we going to figure out whether the series converge or diverge when this is happening? So when this is happening, when the terms become small, how can I tell whether it converges or diverges? And that's what's going to take over the next few sections. But before that, there is I'm going to ask you a simple question. Suppose you have a series and you look at the terms and you realize that the limit of those terms is not 0. So the terms are not going to be small. What can you say about the series immediately? I need answers. Suppose I give you a series You look at the terms and yeah, those terms are not becoming small. What do you think? Diverge, diverge, diverge. Absolutely correct. And this brings me to what we're gonna call test for divergence. So what does the test for divergence tell me? Suppose you have a series. You glance, I mean it, you glance at the terms and you realize that when n goes to infinity, the limit of the an is different from 0. It means the terms are not becoming small or does not exist, but mainly focus on the first part. And you realize that the limit is not 0, then automatically you can say the series diverges. So this is called the test for divergence. So you glance at the an, you realize that don't we come close to 0, you're done, you can say the series diverges. But if they go to 0, you know nothing. We're gonna learn how to decide. So here we have two simple examples. And my question is, for each of the series below, decide if the series converge or diverge. And of course, I'm applying the test for divergence in those. So sigma n equal 1 to infinity, n over to n plus 1. Does this converge or diverge? You know by now the answer. I'm going to look at the general terms, n over to n plus 1. And I say, when n becomes very large, limit as n goes to infinity of the an is limit as n goes to infinity of n over to n plus 1. This is equal to a half, which is different from 0. So the terms of the series are becoming close to a half. It means in your mind, what's happening at the end, you're adding a half plus a half plus a half. So by the divergence test, the series diverges. So immediately, if you glance at the term, it doesn't go to 0, you can say it diverges. And I repeat for the millionth times, if they go to 0, we're going to learn how to handle this situation. So only that, not 0, I can say something. Now, another example for the lack of the limit doesn't exist. Suppose I take this series, minus 1 to the n over for n plus 1. The general terms are minus 1 to the n over for n plus 1. Now, what happened to those when n goes to infinity? Okay, when n goes to infinity, this is minus 1 to the n, always actually kind of a bit hard, but we've dealt with it. We look at this piece. Those are becoming close to 1 over 4. 1 over 4. So the minus 1 over n are going to do the following. All the ans where n is even will be close to 1/4. The ans where n is odd become close to minus 1 over 4. So the limit of those an does not exist in my scenario. The series also will diverge. So test for divergence is an easy test. It just tells you if the limit, if you're lucky enough, you look at the series and your general term doesn't go to 0, then you can say it diverges. You look at the series, the general term equal to 0, you know nothing. That's what I would go for the next 3 sections. We're going to learn what can we do to check whether a series converge or diverge. Questions before I move on? Questions? All right, so what are we now going to do? What's the next step? The next step is the following. If I have a series, first let me tell you one thing. Being able to find the sum of a series is a very hard problem. And most of the time, we don't know how to find the sum. We know it for geometric. Basically, that's about it. Anything else is going to become very hard. But what we will be able to find, what we're going to be able to do is say whether it converges or not. So if it converges, if we know it converges, okay, we can use our computer and find the sum by computing partial sums. If it diverges, it diverges. So what we are going to do now is just being able, we're going to study ideas just to tell us whether converge or diverge, not what the value is, but whether it converge or diverge. All right, the first test we're gonna see today, which help us a little bit for some type of series, is what we're gonna call the integral test for series with positive terms. It means it's a test that helps me sometimes to say whether the series converge or diverge by comparing it to an improper integral. Now remember what the improper integral are. So let me just remind you a little bit, improper integral. Let me remind you the definition of improper integral. Integral from 1 to infinity of f of x dx is the limit as t goes to infinity, integral from 1 to t of f of x dx. That's what the improper integral is. Just a reminder. The integral test is going to do the following. Before I read it, I'll tell you, give you an idea about it. It's going to do the following. Suppose that's what it's going to tell us. Suppose I have a series, let me give you a specific series. Sigma 1 over n squared, n equal 1 to infinity. And I want to know whether the series converge or diverge. I take the following function, f of x equal, so here an is 1 over n squared. I take the function f of x equal 1 over x squared. That's the function I'm going to take. And I'm going to compare the series to the integral from 1 to infinity of f of x dx. And the integral test that, if I have time, I show it the proof tomorrow, tells me that if this integral converge, the series will converge. If the integral diverge, the series will diverge. So it's just going to compare the series to the integral. So I will read it and I will provide you with 2 examples. So a series sigma an is called a series with positive terms if all the an's are positive. And this test only apply when the series have positive terms. And what does it tell us? It tells me the following. Let sigma an be a series with positive terms. And let us say an is f of n, where f is a decreasing function. That's back to the picture here. An is 1 over n squared. That's the function I'm talking about, 1 over x squared. Then the integral test tells me if the integral converges, and we've seen what does it mean for this converge, then the series will follow. It will converge. If the integral diverge, then the series will diverge as well. So we've studied those. So if this converge, the series converge. If the integral diverge, then the series diverge. So that's the first test we're going to see that's going to help us really to determine whether a series converge or diverge. So example. So my first example, I'm going to take 2 easy examples, is use the integral test to decide if the series below converge or diverge. So how are we going to use, so this is my series, n equal 1 to infinity of 1 over n. The an here, it means the terms of it is 1 over n. So we're going to take the function f of x to be 1 over x. F is a decreasing function because the theorem tells me you need f to be decreasing, which is going to be the case most of the time. And we're going to use the integral test and look at the integral from 1 to infinity of 1 over x dx. This integral converge, it means the series will follow through. If this diverge, the series. Sarah asked me, will this test not work if a function is increasing? No, And actually what happened when the function increased, the an will not go to 0. That's what's going to happen. Okay, now we will use the integral test and look at this integral. So let us evaluate this integral from 1 to infinity of 1 over x dx. Definition is the limit as t goes to infinity, integral from 1 to t of 1 over x dx. Now, what's the antiderivative of 1 over x? That's the ln. So it's the limit as t goes to infinity of ln of x from 1 to t. So now I'm just doing something that we've done before. Now let me evaluate this limit. It's ln of t, value at the upper limit, minus the value at the lower limit, which is 0. So this is the limit as t goes to infinity of ln of t. Now, when t goes to infinity, ln of t goes to infinity. So the whole thing goes to infinity. So the integral diverge. What does this mean? Since the integral diverges, the series will also diverge. That's how we work the integral test. So we compare the series to the integral. Now a word about this integral, about this series, because this you're gonna hear it. The series sigma 1 over n has a name, and it's called the harmonic series. So whenever somebody tells you the harmonic series, they are talking about the series sigma 1 over n. So this series diverges, and also note that the terms do go to 0. The terms become small, but the series still diverge. The terms don't become small enough. And this problem puzzled people for a long time. I mean, you guys have heard of Euler, one of the greatest mathematicians. That's where the letter E comes from, of all time. Sigma 1 over n puzzled him because he didn't know about those tests, and he started adding and adding numbers, and the numbers did not grow fast. So he assumed the series converge. And he did a lot of math based on this fact, which were wrong. Till finally they realized that the series diverge. And his confusion was the terms became small, and when he added them up, they did not become large fast enough. You guys can try that. So it really confused him for a long time. He assumed the series converge because it's really not a very intuitive. I mean, we have to work on those ideas. Now, my other example is, which is the last example, I have two simple examples just to elaborate the idea, not let the algebra get into the picture. 1 over n squared, and does this converge or diverge? Now, my an here is 1 over n squared. That's my general term. So my function is 1 over x squared, which is absolutely a decreasing function. Now I'm going to look at the integral, and let us compute the integral. So that's the limit as t goes to infinity, 1 to t of 1 over x squared. Now how to evaluate 1 over x squared? Rewrite it, x to the minus 2, and proceed. So we're integrating again. Now what's the antiderivative of x to the minus 2? It's 1 over minus 2 plus 1, x to the minus 2 plus 1. It means minus 1 over x between 1 and t. So this is the limit as t goes to infinity of evaluation at the upper limit, minus 1 over t, minus plus. So when t goes to infinity, this integral is equal to 1. It means this integral converges. Integral converge, it means the series itself will converge. So sigma 1 over n squared is going to converge. Sigma 1 over n diverge. And tomorrow we see where the split is happening. So sigma 1 over n squared will also converge. But now let us note. The integral goes to 1, but the series itself does not converge to 1. What this tells me only that it converges. It does not tell me the value that it converges to. It just tells me one thing, that it's going to get close to something, but they don't tell me what it is. That's the thing, which is a bit hard for us. So note, sigma 1 over n squared will not converge to 1. The integral test only tells me that it does converge. And we want to find its value, use any computer algebra system, anything you want, and start adding terms. There is no other way out, but doesn't give the sum. Actually, the sum is pi squared over 6, and the proof is very hard. So you have to accept it. But that's the sum. That's the actual sum. The actual sum is pi squared over 6. It's not 1. So the only thing that this test tells me that, yes, it does get close to the fixed number, but does not give me the fixed number at all. It just tells me it converges. But that's already a lot. Okay, so that's the first test that we saw. Actually, we saw 2 tests today. First, the divergence test, which tells me, you know, I take a series. I look at the term. If it doesn't go to 0, I am done, it diverges. But if the general term go to 0, it means those terms I'm adding are very small, then that's what the problem is. Then 2 things can happen. The series may converge or may diverge. So the first test we saw today is the integral test. That's the first test. And we're going to see other tests, you know, this later on. And this test will compare the series to an integral. And tomorrow I'll start by telling you a little bit why this test works. Intuitively, why it is working. Now, it's not really magic. It works. And I will show you why it works tomorrow. But for now, I just want you to be able to basically do the homework. I wanted to say one more thing. I forgot. Anyway, who can tell me what's the difficulty of the integral test? Can anybody tell me what could be hard in the integral test? Okay, don't worry about it. Don't worry about it. Any questions before we close the section? Any questions? Anyone? Okay, so your homework will be on Blackboard in a few minutes. And if you have any problem, you know, I have my office hours right after class. Nobody so far is showing up. But if you have any questions, feel comfortable to join me during my office hours. All right? Anything else? Okay, was the picture better today than yesterday? Yep. All right. Okay, great. Make sure to do the homework and ask me a question. Bye-bye, guys.